Hi everyone, so today we're going to talk about convergent sequences. So full disclosure, this is the kind of stuff that for me when I was first learning these things was very, very difficult for me. So if you find this very difficult, don't worry, you're not alone. This is something that's more to do with a field of math called analysis. And for me, the more algebraic stuff made more sense, and that'll come later. I think next week. I can't wait. So it's likely most of the time people thrive in one and then maybe struggle a little bit with the other, or if you thrive in both, awesome, and if you struggle in both, that's relatable as well. And don't worry, there's many other fields of math as well, other than algebra and analysis. Okay, so let's get into a definition. So a sequence, which I'm going to often shorten to SEQ, just because I try to make my writing shorter. So what is it? It's an index family of sets. So here you see our notation that we've used before. So it's indexed over all the n's and the naturals. So that means in this set we would have A1, A2, all the way forever. So there's an AN for every n in the naturals. But who are these AN? So for each n in the naturals, A sub n is in the reals. Okay. When you go into other classes, you may have sequences that look different than this, but for our class, this is our purpose. And this is a good base to start in, is just thinking about sequences in the reals, and then maybe later on in life you can expand from that in your mathematical career. So given some natural number m, the number a sub m is called the mth term of that sequence. Okay, so here's a few other ways that you might see sequences written. So we have that one, and then we also have maybe this. So you have like, so it's kind of like the summation. You start at 1, you go up by intervals until you get to infinity. And then sometimes people put them in parentheses. Okay, and then same deal, maybe they'd put these on the parentheses. Although that would be kind of agitating to me, because it almost looks like you're raising it to the infinitieth power, which really doesn't make too much sense. But also, some people write it without the index, which to me is a little bit, I don't know, nerve-wracking, honestly, because how are you supposed to, yeah. Anywho, so one question you might have is, well, what the heck, Danica? Like, how do we even know anything about these ANs? And that's a good point. So typically, instead of writing AN, they'll actually write an equation in it. So let me give some examples. So one example is just n from 1 to infinity. Okay. That's going to be 1, 2, L. So this is the Lth term. Okay, and then it just goes on forever. Okay, so let's continue with our examples. So in this next one here, there's no relationship between the formula and our indexing. So this ends up just being 1, 1, 1 forever and ever. Okay, how about the next one? Okay, well this one, something is changing. So our first natural number is 1, so we get -1. And then 1, then -1, so on and so forth. So this one, okay, well, our first one is 2 minus 3. Okay, our second one is 2 times 2 minus 3 squared. On and on and on. Okay. Yes. So another way that we could write this one above is we could say, well, we could do a piecewise function type situation. So it's not exactly like that, but it's a piecewise definition. So we could say a sub n equals 1 when n even, and a sub n equals -1 when n is odd. And so that covers all of our situations that could happen. All right, so mathematicians as well as many other professions care about patterns, but more than that, people really care about when patterns somehow converge. Okay, so maybe like at first it's a little hectic, the pattern, but then it starts to kind of even out into more of a flat kind of curve looking, if we plotted all the points of an. Okay, so now let's introduce what the definition of converges. Okay, so this is a very long definition, I understand. So basically what this is we let ANs form a sequence, and we let L be a real number. So L is kind of our secret way of saying that that's our limit, okay? Well, we say that our sequence of ANs converges to L if for all epsilon in the positive reals, okay, so epsilon has to be bigger than 0, there exists some n in the natural numbers, capital N, such that for all little n in the naturals with little n greater than or equal to capital N, we have that the absolute value of an minus L is less than epsilon. Okay? Now I know that looks totally crazy, right? Probably to a lot of you. So let's break it down. So you get handed a sequence, and maybe someone also tells you, okay, well, this is what the limit is. So let this be your L. Well, if that really was the limit of your sequence, if any evil scientist hands you some epsilon that's bigger than 0, and so we tend to imagine that epsilon is kind of small, right? Because that's after I explain more, it'll make more sense, because it doesn't matter if it's big. If epsilon is big, then you're not really saying much, okay? So epsilon, think of that as our margin of error, okay, if that makes sense. Okay, so some evil scientist hands you some epsilon greater than 0. Then there exists some, you should be able to find in your sequence that there's some capital N, which at that point, so at that capital Nth term, that term and every single other term after that are within epsilon of your limit. Okay? All right, so I'm going to write it in symbols, and then we can talk a little bit more. All right? So in symbols, we have for all epsilon in the positive reals, there exists some capital N in the naturals. Okay? So for each epsilon, there corresponds a capital N. These capital N's could be different based on who epsilon is. Okay, but this is what we have. There exists an N such that for all little n in the naturals, where little n is bigger than or equal to capital N, didn't give myself enough room, an minus L is less than epsilon. Okay, this is very important definition, and you should eventually memorize this. Okay, this is a very important definition. You should eventually memorize this. Okay? All right, so we call L our limit, but I will warn you right now, you're not taking the limit of anything. Okay, I don't want to see anything like this limit of an stuff. Okay? No. No, thank you. Okay? I'll explain more about that later, but just going to mention it every chance that I get so that hopefully everyone hears me at least once. Okay, our limit of the sequence. We say that such a sequence is a convergent sequence. And if it doesn't converge to L, to absolute value of L less than infinity, okay, so L has to be finite, that's the other thing. And remember, L is a fixed number. So if it doesn't converge to absolute value of L less than infinity, then we call it a divergent sequence. Okay, so you might be excited. Oh, we learned about this in calc, or maybe you're learning about it right now in calc. But unfortunately, you won't be able to use a lot of those tools that you have, like the lim that I talked about before. So kind of how I like to explain to people, at least beginning of analysis, is proving that calculus is true. Okay, proving that those tools that you use and all those things actually do give you what you want, or that they work, just things like that. Okay, so you're not allowed to use calculus in that way here. My last 2 semesters teaching this has always been a very difficult topic for my students. So I came up with this kind of silly example, but hopefully it helps a little bit. So what you're going to do is you're going to consider a machine that flips a coin. Okay, so heads, the machine calculates +1. Don't ask me how the machine knows. It just has eyes or something. I don't know. It's never wrong. I don't know. So heads is +1, tails is -1. Okay, so now we will have a sequence and in the naturals, right? Because it has a first time and it just keeps going on and on forever. Okay, all right, so let's say the first time, so let's say this is 1 and this is -1. So first time it hits heads, second time tails, maybe tails a few times, and then heads. Okay, so see, so it's just kind of all over, just as you would expect it. Okay, now let's say, so those are just supposed to be dots. So let's say we go down the line and all of a sudden you have this pattern where it does heads like a bunch of times in a row. Let's say like it's 20 times or something, I don't know. Well, you might be itchy to say that this sequence does converge, because look at, so our limit would be 1, okay, and maybe our natural number n is, so maybe this is the kth time it flips or something. So we might be like, okay, well, maybe limit equals 1 question mark, and then our capital N from our definition before would equal K. All right, so then any, oh, wait, but if we return back, okay, we need it then that all the little n's are bigger than or equal to capital N. Okay, so this epsilon thing, I'm not really worrying too much about it, because epsilon, what that does is it allows you some buffer. It allows you some margin of error. So here would be 1 plus epsilon, here would be 1 minus epsilon. Okay, or L plus epsilon, L minus epsilon, at least in our case. So, okay. So epsilon gives us some buffer, and well, we don't really need a whole lot of buffer if they're all just going to actually be equal to 1 forever and always. But that's the bummer. We don't know that it's going to be 1 forever and always. Okay, so we do have to actually follow through and watch the machine over and over and over again. And then maybe we do ... and then maybe like in the Lth position, boom, it got a tails. Okay, now we lost our capital N, okay, because L is bigger than capital N, or K, and A sub L minus 1. Well, remember, epsilon is teeny tiny. So if you pick epsilon to even be 1/2, which is funny to say, but that's humongous. Epsilon, usually what we're thinking about is we're thinking so minuscule that it's basically 0, but we still let some wiggle room happen. So even an epsilon as big as 1/2, because typically what we do, if 1/2 is huge, we typically always say it's less than 1, okay? So for epsilon 1/2, this doesn't work. Then holy guacamole, this isn't going to work for our tiny epsilons, okay? Okay, so this is probably going to be not convergent. Okay, so this was kind of a silly example. Now let me give you an example, and I won't actually define what the ANs are, like explicitly, but maybe I'll like plot them on the graph. So maybe this is 1. Okay, so, and maybe it continues that pattern. It keeps swiveling a little bit, but the swivels get smaller and smaller and smaller or something. Okay. Well, all right. Let's say that this is, I don't know. We could pick something real. We can say like 10. Okay. So 10 is our best guess from this graph as our limit. So now I want you pick any epsilon you want, as tiny as you can possibly think of it. Okay. I'm talking smaller than Horton Hears a Who kind of stuff. Okay, so we get super, super tiny. No matter how small we get, we want to be able to find a capital N such that all of our ANs with n bigger than or equal to n to be inside of it. Okay, I know it sounds like a lot. So let's start from the beginning. Let's choose an epsilon. So let's say that purple epsilon, or epsilon 1 maybe, is kind of a beefy epsilon. Okay, so this is 10 plus epsilon 1. This is 10 minus epsilon 1. Okay, so for epsilon 1, who could we choose as our capital N? Well, we could choose this one here, but, you know, what's stopping us? We could choose that one. Like if we didn't have all our information about these things up front, or, you know, our stuff with AP, oftentimes we're just picking something. We don't need to pick like the closest or whatever. We just need to pick something. But these 3 will not work. Anything after that will work as our capital N. Okay. All right. So let's pick, I don't know, let's pick this one. So maybe I'll call that N1. Okay. So now I want, for all natural numbers that are bigger than or equal to n1, do we have that an minus 10 is less than epsilon? Question mark? Well, yes, according to the graph, that's true. Because every single one afterwards, and so we're pretending like we do know what this function looks like forever and always. Okay, this is not like our flipping a coin where so much is left up to chance. Okay? So we do know, because we know that every single an is within these purple bounds after capital N1. Okay? So yes. Oh, sorry, epsilon 1. Yeah, so this is our purple example. Okay, well, how about if green epsilon is a little bit smaller? I'm not very good at making up graphs or drawing. But bear with me. Let's say that this is epsilon 2. So this would be 10 plus epsilon 2. So, interestingly enough, it looks like we might be able to choose that one, but we can't because this. So similarly, we can't pick that one either. Okay? So the first one we could pick is this one, but we could also pick someone way down here. That's fine as well. So I hope that this is making a little bit more sense to everyone. It is tough. It's a tough topic. Okay, all right, I would like to end this with, I repeat, do not use limits in your proof. You can use L, but you cannot use limits in your proof. No. I know this sounds confusing, but the only limit you should talk about is L. If you write something like lim an as n goes to infinity equals, and then you say what it equals, okay, because you know by calculus, so maybe you say 6 or something, I don't know. If that is your proof, at least in past semesters, you will get 0 points because you have not demonstrated that you know the definition or that you know how to work the definition. This is fine to do in your head to try to figure out who you want your L to be, but it should not be on your paper. Okay? We are trying to get you to do proofs with our definition, not with this that you learned in calculus. Because remember, like I said before, at least the beginning of analysis, typically what people teach is we're proving the things in calculus to be true, okay? So for our purposes, we wouldn't know that this is the case. You need to prove it with the bare bones, okay? And it would be really good practice because in the future of your mathematical career, there will be way more intense things to do with sequences. Okay. All right, have a good one.